for which we need the controller. First one is to suppress the influence of external disturbance. Second one is to ensure the stability. And third one is to find the optimal operating condition for the best performance of a process. And first issue we already discussed. Now just let us conclude this. So to discuss the influence of external disturbance, we have adopted one liquid tank system, which is very perhaps the simplest example. And we have seen that here disturbance is this inlet flow rate Fi. How this inlet flow rate affects the liquid height in the tank. Okay, and that can be taken care of by properly adjusting this outlet flow rate capital F. So this is open loop schematic for the example liquid tank system, because it does not include any controller, and here we have just included the control configuration here. That's why it is called closed loop liquid level system. Fine. Now let us come to our second issue, that is to ensure the stability of a process. First you draw this graphical representation, then we will discuss. Draw this graphical representation of a stable process, which is shown in the left hand side. So along the y-axis we are considering x. X means it may be temperature, maybe pressure, maybe concentration, and along x-axis we are considering time. Recall that we first start a process and then we bring that process to steady state. After achieving steady state condition, I mentioned in the last class, we employ the controller. This is the usual, way we employ the controller. I repeat, first we start the process, then we bring that process to steady state condition. Now the time required from starting to achieving steady state is called startup period. Fine. We start the process, we bring that process to the steady state. The time required for this is called startup period. Now after achieving steady state condition, we employ the controller. This is the usual technique which is followed in for industrial units. So accordingly, you see, I have shown one horizontal line here. This horizontal line basically indicates the process is at steady state condition. SS means steady state. That means there is no deviation in X. Now at a particular time instant T naught, this process is irritated by a disturbance. Fine. And because of that disturbance, the process output X starts oscillating. And if you see, this oscillation is with decreasing amplitude. It is quite obvious that the process output, after getting disturbed by an external disturbance, it is coming back to the original X. That's why this process is called self-regulating process. I repeat, Initially, the process is at steady state condition, which is represented by this horizontal line. Then after a particular time instant t0, this process is irritated by an external disturbance. As a result, the X starts oscillating, you see, but the oscillation is with decreasing amplitude. That means it is coming back to the original X. Therefore, this type of process is called self-regulating process. Fine, and it is stable process. For such a situation of a process, we don't need any controller because it is automatically coming back to the original X. And this is an example of a stable process. Now question is, for this stable process also I want to employ controller. I repeat, for this stable process also I want to employ a controller. Can you tell me what is the, I mean, why what profit I will gain from this? What is the gain by employing a controller for this stable process? Anyone?
So the time between T naught and the next instant when the process will be back at steady state will be reduced.
Very good. What's your roll number?
So 19CH 30034.
Very correct.
And sir, it might happen that the new steady state is something different from the earlier steady state.
Correct. What's your roll number?
So 19CH 30024.
Very good. You both are correct. So that's why we want to use one controller. Fine. I have written, in fact, these 2 points, you see. First one is controller leads to reach the process to steady state with a shorter time. Basically, this we can call as settling time. Fine. Settling time and the time at which the process is irritated with external disturbance. This time period, if we want to make shorter, we can use one controller. That means we can achieve or come back to the steady state faster if we use a controller. This is the first point. And second point is what you told. You know, you can understand this physically also. For this, let us take the liquid tank example system. Okay. For the second point, uh, you can easily understand this by taking one example. Suppose we can continue with our liquid tank system. Our input is Fi. This is the process. Input is Fi, output is F. So what happens if I suddenly increase Fi? The height increases. Agree? And if height increases, there is a hydrostatic pressure, which is H rho G, because of that increased height. And that hydrostatic pressure leads to increase the outlet flow rate F. But this height reaches a new steady state. I repeat, this is a simple liquid tank example system. If we increase suddenly this Fi, which is nothing but an external disturbance, the height increases. And if height increases, the hydrostatic pressure increases, which is estimated as H rho G. And because of that increased hydrostatic pressure, this outlet flow rate also increases. But whatever may be, this height already reached a new steady state. But you know, we want to maintain a particular HSP set point. We do not want to continue with the new steady state. So if we want to come back to the original steady state from this new steady state, we need a controller. Or other word, I can say the controller does not permit to achieve a new steady state. Fine. There may be a little bit oscillation, then it will come back to the old steady state. It's not going to settle in a new steady state. So these are the main two reasons. Even for stable process, we use controller. I hope it is clear to everyone.
Yes, sir.
Okay. Now come to unstable process. Unstable process is very obvious based on our previous discussion on stable process. Explanation is quite similar. You see, the process is initially at steady state condition, and then at a time instant t naught, this process is irritated by an external disturbance. As a result, there is an oscillation with increasing amplitude. So it is not coming back to the original steady state. That's why this is called unstable. I mean, this is the example of an unstable process. Fine. And in this case, our objective is quite clear. We want to come back to the original steady state. We do not want this oscillation. Or even oscillation is there, it must be with decreasing amplitude, not increasing amplitude. And this can only be done by the employment of a controller. Fine. So this is our second issue, and that's why we need to use controller. First one was to suppress the effect of disturbance. Second one is to ensure the stability. Both are clear to us. Next we will go to optimize the performance of a process. Okay, let us first discuss how we can optimize the performance. In the last class, we discussed about the requirements for a particular process. The requirements are listed as safety. That was the primary requirement we mentioned. Second one is product specification we need to maintain. Third one is environmental regulations. Fourth one was operational constraints. And fifth one was economics. Okay. So first one is safety, second one is product specification, and last one is economics for us. But you know, for the investor, it is just reverse. They first think about the profit, which is our last requirement. It is their first requirement, profit. And our first requirement is safety, and the safety is the last requirement for the investor. Okay, it's quite unfortunate. Anyway, so let us discuss this economics. To discuss this, let us adopt one example system, which is shown here. You see, you draw this schematic of a continuous starter tank reactor. Then I will discuss. Draw this schematic first. Okay, now let us discuss this process first. See, this is a jacketed continuous starter tank reactor. I think you have started this in your reaction course. Now reactant is introduced. So this is the inlet stream, which is nothing but the reactant, and reactant is here component A. Reactant means component A. And this reaction, consecutive reaction occurs in this reactor. This is basically overall an exothermic reaction. As I mentioned, A is our reactant, B is the desired product, but we get also C, which is undesired product, or better to say undesired waste. So here our objective is to produce as much B as possible. Fine. And since this is exothermic reaction, we need to take out this exothermic heat from this CSTR to maintain the temperature at its desired level. I repeat, for this example CSTR, we want to maintain the temperature at its desired level. But this reaction is exothermic reaction. So exothermic heat is all the times produced. Now we need to take out that exothermic heat to maintain the temperature at its desired level. How we can do that? By using a coolant stream. You see, which is shown here, it is flowing through this jacket. Fine, that's why we are using coolant stream. Okay, now can you tell me why the coolant stream outlet is at the top and inlet is at the bottom?
Because the hot water has more density, so.
Anyone else? Any better answer?
Because the coolant will rise automatically to that level due to heat. Its density will get reduced.
Anyone else?
Sure, so that we restrict the flow in downward direction due to gravity.
Okay.
Sir, the heat in the lower portion will be greater than the upper portion. That's why it is flown from the downward to the upward.
Heat evolved will be more, you are saying?
Yes, sir. Heat evolve will be more in the downward portion than the upward portion as the upper lid is opened.
So why the stirrer is given there then? Stirrer is given mainly to maintain the uniformity, no?
Yes.
Anyway, I think you gave some answer based on your, I think, 10+2 concept. But technical answer is still, I did not get. Anyway, you try for this. Okay. Why it is like this? Try to find the answer for this. Okay. Now, what is our economic objective? You see, this is our economic objective. Here phi is basically the profit. We want to maximize the profit. So what is basically profit? How much we earned by selling our product B minus expenditure. What is expenditure? Expenditure in terms of raw material and expenditure of other operating cost. Fine. And 0 is our starting time in the integration. 0 is our starting time, and T capital R is the operating time or run time. How long we are running the process. Fine. So how much we earned by selling the product minus our expenditure. Here expenditure includes cost of raw material and other operating cost. Other operating cost means utility cost, coolant is there, steam is there, electricity is there, etc. And definitely labor, engineers, all are there. Fine. But this is just the representative term, because here we did not consider any cost related to initial investment. We did not include cost related to piping. Okay. So just to understand this concept, it's briefly highlighted here. Okay. And we do this from starting time to our total operating time. So this is your economic objective, and based on this economic objective, I mean to maximize, our target is to maximize the profit, and based on this equation we can find the best operating condition, what temperature, what pressure we can operate this process. In fact, sometimes we find the dimension also, design actually. Okay, so these are the three important issues which are taken care of by the controller. Any question? Otherwise, we'll go to the next topic. Jyotiraditya, any question you have?
No, sir.
You understood everything?
Yes, sir.
Good. So let us go to the next topic then. Fine. Before going to the next topic, you can note down these questions. Basically, I discussed the answer of these three questions, but still you can note down these three questions. Adrija is there, Adrija Rai.
Yes, sir.
Yeah, can you tell me what is the difference between open loop process and closed loop process?
Yes, sir. Sir, an open loop process is the schematic of a process without a control configuration, and a closed loop process employs a control configuration to achieve the desired set point values.
Correct. Shivam Raj, are you there?
Yes, sir. Yes, sir.
Can you tell me what is control configuration? What do you mean by control configuration? How it makes the process different?
Sir. It is activity of managing the product
Sorry,
through
repeat. Activity of?
managing the product throughout the life cycle of product.
So from where you are extracting this answer? From which subject? Anyway, you go through the notes, okay? Okay, let us come to the next topic, that is, variables. Okay, we want to know the classification of variables, and what classification of variables I'm going to show here. It is exclusively true for process control course. Remember this. The classification of variables which I am going to show or discuss here, this is exclusively valid for process control course. Fine. Now, variables we can classify into two categories: input variable and output variable. Now, input variables are again two types. Input variables are again two types. One is MV. MV means manipulated variable. MV means manipulated variable, or it is also called as control variable. Fine. And another class is LV. LV means load variable. Load. LOAD. Or disturbance variable, or simply disturbance. I repeat, input variables are classified into two categories. One is manipulated variable or MV. It is also called as control variable. And second one is LV, means load variable or disturbance variable, or simply disturbance. Now this disturbance variable is again two types. One is measured load variable or measured disturbance. Another one is unmeasured disturbance. Disturbance variable is again two types. One is measured load variable or measured disturbance, and unmeasured load variable or unmeasured disturbance. It is very simple. For an industrial process, there are so many disturbance variables. So we do not go to measure all of them because cost is involved in measurement, no? So which are exclusively required for us? The information for few load variables we really need to evaluate the process performance. For those load variables only we go for measurement. For other load variables we do not measure. Okay, I mean we do not measure other variables. So that's why it's a measured and unmeasured load variable. Now you note down the output variables. Output variables are again two types. One is measured output, another one is unmeasured output. It is like measured disturbance and unmeasured disturbance. That means few output variables we measure and few output variables we do not go to measure. Now among the measured output variables, again we have two types. One is primary measurement, another one is secondary measurement. Measured output variables are again two types. One is primary measurement or primary measured output, and another one is secondary measured output. And this primary measured output is usually called controlled variable, CV, controlled variable, CV. Now I want to mention one point here that many times the student mix up with this control variable and controlled variable, you see. But you remember they are different. They're totally different in fact. Okay, do not confuse with these terms. Control variable and controlled variable, they are totally different. So what I want to mention here that from today onward, I mean from the next discussion onwards, we'll use these variables exclusively. Okay, we'll discuss this process control content from now onwards with the use of these variables. So you have to keep the name of all these variables in your mind all the times. In most of the cases, I have seen that if you, I mean, many students, they do not remember these and they cannot understand many simple things even. So you remember the name of these variables in your mind all the times. And as I mentioned, this variable table, classification table is exclusively valid for process control course. Fine. It does not mean that, the variables are input, two types input and outputs, they are nowhere. They are there, but, few things are exclusively useful for process control, like this load variable, control variable. These names we cannot find in other courses. That's why I am telling all the times that this is exclusively true for process control course. Now we will discuss with adopting a couple of examples to know all these variables and their uses. Fine. One by one we'll know with example system. Let us take this simple example first. You draw this figure. This is a liquid tank system. Let us discuss how we can define the variables for different chemical processes. And at first, we are adopting a simple liquid tank system. Here, as I mentioned, Fi is the inlet flow rate, and F naught or Fo is the outlet flow rate. Fi is inlet flow rate and F naught or Fo is outlet flow rate. H is the liquid height in the tank, and capital A is the cross-sectional area of the liquid tank. Capital A is the cross-sectional area of the liquid tank, which is basically here cylindrical. Now, at first, we have classified the variables into two categories. One is input, another one is output. So obviously here Fi is the input variable and our H and F naught, they are output variables. Fine. So this is, or this classification we can make for the open loop liquid tank system. And in the next phase, we will classify the variables for this example system in closed loop case. Okay. You draw the closed loop configuration first. Closed loop schematic you draw, then I will discuss. This closed loop liquid tank system we already discussed. Fine. Only difference here is that instead of F naught, Fi we are controlling, or Fi we are adjusting, it is better to say. Drawn this, Ronak Agarwal. Drawn this figure, Ronak. So you're not present. Okay. Okay. Now in the last class, what I told, whenever we are taking one example system in this process control course, our first job is to identify the control objective. Okay. So for this liquid tank example system, our control objective is to maintain the liquid height at its desired set point value, which is written here. Fine. I repeat, whenever we are taking an example system for controller design, our first job is to identify the control objective. Now for this example liquid tank system, our control objective is to maintain the liquid height in the tank at its desired set point value, which is written here, you see. Now second step is to find the control variable, manipulated variable pair. This is the second objective. We need to find or identify the control variable, manipulated variable pair. So if you fix your control objective, like for this example system, height is the control objective. So you straightforward way put the height under control variable column. This is a straightforward way you can follow. I repeat, if you fix your control objective in terms of a particular variable, you consider that variable as control variable. Clear? Now you need to find the corresponding manipulated variable. This manipulated variable you can find through physical understanding. Theoretically also it is possible. I'm coming to that point. But before that, physically also you can understand this. Like height we want to maintain. Now this height we can change. I mean, we can increase or decrease by changing Fi. So Fi and H, they are directly correlated. And in that way, we can fix Fi as manipulated variable. Fine. So theoretically, it is somewhat like this. Control variable and manipulated variable, they are selected such that they have direct and fast effect. I repeat, control variable, you can note down this point even. Control variable and manipulated variable is selected such that the manipulated variable has direct and fast effect on control variable. I repeat, control variable and manipulated variable pair is selected such that the manipulated variable has direct and fast effect on control variable. Fine. Then in the next step, you draw this configuration. In the next step, you draw this configuration. It is, as I discussed, control variable is height. So you first measure this liquid height, employing one sensor. Here the sensor is differential pressure cell, DPC. Then this DPC gives us the measured height, which carries negative sign, and set point value, which is fixed by us, it has positive sign. So we compare this set point with our measured height in this comparator. It's nothing but a one-line program. That is E equal to HSP minus H. This is one-line program you need to include in your computer. So comparator is basically represented by one-line program. Fine. Then this gives us error signal. This error signal goes to controller. Then controller has basically represented by, this controller is represented by a couple of lines program. and it basically calculates the control action. What should be Fi? This controller calculates it. And then that control action is physically implemented through this valve. Fine. So this is the closed loop operation of the liquid tank system. I repeat the steps again. Whenever you are taking a process for controller design, your first job is to identify the control objective. For this example system, our control objective is to maintain the liquid height in the tank at its desired set point value. Your second job is to find the control variable manipulated variable pair. How we can do that? The control objective you have fixed in terms of a variable that you put in this table as control variable. So height is our control variable. Now what should be the corresponding manipulated variable? That we can do from our physical understanding. It is somewhat like this. This height must be affected with the manipulated variable. If they are not affected by each other, you cannot make this pair. Fine. It is very clear that this height is increased if we increase the Fi. In contrary, this height decreases with the decrease of Fi. So they are definitely correlated to each other. So we can make this pair as control variable, manipulated variable pair. This is from physical understanding, and theoretically there are many points, but at this starting level, no, I can highlight or I can mention only one point. That is, control variable and manipulated variable pair is selected such that the manipulated variable has direct and first effect on control variable. So this making this table is our second point I told, and in the third point you just make this configuration. So how we can do that? This height is already selected at control variable. So first you measure it employing one sensor. Here it is differential pressure cell. Then this measured height is compared with its set point value in the comparator, which is just one line program, that is E equal to HSP minus H. Then this error signal goes to the controller. The controller calculates what should be Fi. Other word, this controller calculates control action, and that control action is physically implemented through this control valve. So like this way, we do the closed loop operation. Yeah, do you have any question?
Sir, is FO here an unmeasured output variable or secondary measured output variable?
FO is, here output variable, and if you want to know the flow rate of F naught, you can measure it.
Okay, sir.
It's not primary or secondary. It's the measured or unmeasured. Primary, secondary, I think you just wait for a couple of, maybe in the next class. Be either measured or unmeasured. If you want to know the information of F naught, you measure it. If you don't need, you do not measure it. That's it.
Okay, sir.
Yeah, any other question from anyone? Okay. If you do not have any question, I am asking one question. You see, this is the original liquid height. Fine. But after measuring this liquid height, I have written here the same H. So what do you think? These two are identical or different? I repeat the question. Liquid height I have written, or we are denoting by small h. And that height we are measuring by one sensor. After measurement also I have written the liquid height with the same notation h. So what do you think? These two heights are identical? or
different.
Different. Correct. Practically they are different. Fine. But here we are assuming they are identical because there is certain measurement noise or measurement errors. Practically these two H are not identical, but here we are assuming identical. Fine. Okay. I think one of your friends, he mentioned in the last class that instead of F naught, we can use Fi as manipulated variable. Fine. And I told in the last class that we will discuss this issue later. So this is the discussion. I mean, to control this height, you can manipulate either Fi or F naught because they are directly correlated. In fact, I am going to discuss in the next example, you see. You just draw it. I think it's straightforward. You can easily understand this. Same example, only difference is that here instead of Fi, F naught is considered manipulated variable. That is the only difference. So as I mentioned, for an example system, we first identify the control objective. Here it is H equal to HSP. Our second job is to find the control variable, manipulated variable pair, and that is here H versus F naught. Our third job is to develop the system or closed loop system. Fine, that means we need to just include the control configuration with the example process. This is our third job. But our topic is we are discussing currently about variables classifications. So that's why I have written at the end you see inputs and outputs. Yeah. Do you have any question here in this example? Shomik, Sarkar,
Yes, sir.
do you have any question?
No, sir.
If you do not have any question, you tell me why if not is considered input. You see, if not, I have written under input. Why?
So because we are regulating that variable.
Regulating means?
The
Just
controller.
elaborate. Yeah, elaborate.
Controller is like the controller controls the flow rate of the output. So we are in control of that flow rate only. If I can vary or have any disturbance, which we are not controlling here.
Now, can you define based on the classification table we make or we discussed? I mean, I need very straightforward answer.
If not is we manipulate that variable, so we can
Yes.
consider it as manipulated variable, which is under input variable.
Correct. This is a straightforward answer. So do not be confused. Your manipulated variable always falls under input variable. Fine. So that's why F0 is considered here as an input. And again, I want to mention here, that's why I told this is exclusively true for process control course. Originally, you see F0 is output variable, but whenever you are going to employ one controller with considering F0 as manipulated variable, then you have to consider F0 as input variable, because manipulated variable falls under input variable according to the variable classification table. Agree? Anyone else? Any question? Okay. If you do not have any question, it's okay. Let us end today. Thank you.
Thank you, sir.
Thank you, sir.
Thank you to everyone.
Thank you, sir.
Thank you, sir.